Hello friends, I welcome you in lecture number 40 on double integrals. In this lecture we are going to discuss about substitutions in double integrals. How to select proper substitutions so that we can apply the change of variables in double integrals. We have already studied about change of variables in integrals of functions of one variable. We just recall that how we can apply the change of variables in integral of functions of one variable. We consider this integral of x cube times square root of x square minus 1 with respect to x. Limits of integration are from 1 to 2. So here if we want to evaluate this integral, we can consider this change of variables. We can use this substitution. We can replace x square minus 1 by some new variable, say u. That is, we are changing the variable x to new variable u. So we have to convert everything which is in terms of x, that we have to write in terms of new variable u. So from this I can take derivative on both sides with respect to x on this side. So I will have 2x dx equal to du. So therefore I will obtain x dx equal to 1/2 times du, and here this x cube can be rewritten as x square into x. So we can split this into two parts, x square into x, and this x into dx will be replaced by 1/2 into du. And for x square we can write from this, x square can be written as u plus 1. Now because we are changing the variable by this substitution, we have to find out limits for new variable also. So for that we can use this u equal to x square minus 1 when x is 1. If we take x equal to 1, we will have u equal to 0. For x equal to 1, u is 0, and when x is 2, we will have u equal to 4 minus 1, that is 3. So if limits of x are from 1 to 2, limits of u will be from 0 to 3. So finally our integral will be transformed into the new variable u, whose limits are from 0 to 3. This x cube is written as x square into x dx. X square is written as u plus 1, and this under root of x square minus 1 is under root u, and dx x dx will be replaced by 1/2 into du. Now we can multiply this u plus 1 with square root of u, and we can easily integrate in powers of u. Here u into square root of u, that is u raised to 1 plus 1 by 2, that is 3 by 2, plus u raised to 1 by 2, and this 1/2 we can take outside. So this is just to explain that how we can apply change of variables in integral of functions of one variables. We are doing to generalize same thing for functions of two variables, that is for double integrals. Suppose I have double integral of function of two variables over some region R. Then suppose I am not able to integrate this function in terms of variables x and y, but by applying some transformation I can change these variables to new variables, and in new variables I can easily integrate this function. For example, if I consider x as a function of new variables, say u and v, y as a function of u and v. Suppose x and y are converted in terms of new variables u and v. Then I have to convert this function in terms of u and v. So I will replace x by g of uv. I will replace y by h of uv. and I have to find out that what will be this dx dy. So dx dy will be equal to absolute value of Jacobian with respect to uv and times du times dv. So what is this capital J that we are going to discuss? But we will remember that this dx dy will be replaced by absolute value of the Jacobian times du dv. Now as we have discussed here we are changing the variable x to new variable u. So we have to find out limits of integration for u also, or we can say that here interval of integration was 1 to 2. For limits of x we can say that x lies in the interval 1 to 2. So here region of integration was interval 1 to 2, but in this case region of integration is close interval 0 to 3. So region of integration is also changing. Here we have integral from 1 to 2, integral over this interval 1 to 2. Then with respect to u we have integral over the interval 0 to 3. So this shows that region of integration is also changing. Region of integration in old variables is transformed into the region of integration into new variable. Same thing will happen here. This is the region of integration for old variables x and y, or we can say that R is the region of integration in xy plane, and that region of integration will be transformed into another region of integration in terms of new variables u and v. So we have to find out the corresponding region of integration into uv plane. So this region R will be transformed into some another region, say G, and here we have to find out limits of u and v to integrate with respect to uv. Here integral is with respect to x and y. So for this we are using the region R. Now because we are changing the variables from x, y to new variables u and v, so this integral is over some new region G in uv plane. So we have to find out what will be the region G in the uv plane under this transformation, and what will be the limits of integration for new variables u and v. So we will discuss all these things with the help of examples. Now here we will remember that dx dy will be replaced by absolute value of j with respect to u and v. So what is this j? So because we have taken this change of variables using this transformation, x is function of u and v, y is also some another function of u and v. So here x and y are functions of two variables u and v. So we can find out partial derivatives of x and y with respect to u and v. So suppose we write down the determinant whose first row is partial derivatives of x with respect to u and v, and second row is partial derivatives of y with respect to u and v. So we are writing partial derivatives of x and y with respect to u and v, and we are constructing the determinant of these partial derivatives. This determinant is known as Jacobian of x, y with respect to u and v. This is the notation for Jacobian. It is denoted by this notation also. Some books are using this notation also, j in the bracket uv. U and v are independent variables. We are taking derivatives of x and y with respect to u and v. So we will remember that if x is a function of u and v, y is also function of u and v, then Jacobian of x and y with respect to u and v is given by del xy over del uv. This is another notation j. We can use this notation also. but we will remember that it is the determinant. Determinant having 2 rows and 2 columns. First row stands for partial derivatives of x with respect to u and v. Second row stands for partial derivatives of y with respect to u and v. We can understand this definition with the help of example. Suppose I consider x equal to u minus v, y equal to u plus v. Then suppose I want to find out Jacobian of xy with respect to u and v. Then I have to first write down the definition. First row is partial derivatives of x with respect to u and v. Second row partial derivatives of y with respect to u and v. X is u minus v, so if we differentiate with respect to u, we will consider y as v as constant. So derivative of x with respect to u is 1 minus 0, that is 1. Derivative of x with respect to v, we consider u as constant, so 0 minus 1, that is minus 1. Similarly, partial derivative of y with respect to u is 1, and partial derivative of y with respect to v is also 1. And we simplify this, or we evaluate this determinant. 1 into 1 minus 1 into minus 1, so we can see Jacobian is 2. So it is easy to find out Jacobian of this type of transformation. We can have x and y as functions of 3 variables also. So in that case we can have 3 variables. Dependent variables are 3, x, y, z, and x, y, z can be functions of 3 independent variables u, v and w. So we can evaluate Jacobian of x, y, z with respect to u, v, w also, and that will be the determinant of order 3. So that we will discuss in the topic of triple integrals. Here we require Jacobian of 2 dependent variables x and y with respect to 2 independent variables u and v. Now sometimes we can write down u and v in terms of x and y also. We can express u and v in terms of variables x and y. So in that case we will have Jacobian of u, v with respect to x, y. So this we can denote by j dash. So if we multiply these two Jacobians, Jacobian of x, y with respect to u, v and Jacobian of u, v with respect to x, y, then their product is always 1, or we can say that j times j dash is always 1. So sometimes what happens, suppose we are considering this transformation, x is a function of u and v, y is a function of u and v, and suppose it is easy to calculate this Jacobian of u, v with respect to x and y. Then we can calculate this Jacobian first, then Jacobian of this will be equal to 1 divided by this Jacobian. So we can use this property sometimes if it is not easy to find out Jacobian of xy with respect to u and v. So the main thing is that how to employ the change of variables in double integrals. So suppose we have double integral of function f with respect to x and y over some region R, and suppose we are considering this transformation, x is a function of u and v, y is also another function of u and v, then this will be converted into double integral with respect to u and v. So for that we have to convert everything in terms of x and y. So in the given function we will replace x by this function g of uv, y by this function h of uv, and this dx into dy will be replaced by absolute value of Jacobian times du dv. So this is important, we will remember dx dy will be replaced by absolute value of Jacobian times du dv, where j is the Jacobian of xy with respect to u and v. And of course this region will be transformed into some another region G in the UV plane. So what we are doing here we have XY plane, here we have UV plane. So suppose we have some region, this type of region, suppose this is the region R in XY plane, then that region can be transformed into another region, for example rectangular region in the UV plane. So suppose this is G. So we will see this type of problems in upcoming lectures. For the time being you have to remember what is Jacobian, and if we apply this substitution in double integrals, or if we apply this change of variables, then we have to remember this formula. Dx dy will be replaced by absolute value of Jacobian times du dv, and this function fxy will be converted into function of u and v by replacing x by g of uv and y by h of uv. So that formula is known as change of variables formula for double integral. I have written here systematically. Let x be a function of u and v, y be another function of u and v. Suppose this transformation define a one-to-one mapping of a region G onto a region R in the xy plane such that Jacobian of xy with respect to uv is never 0 on G. This quantity is never 0 on this region G. Then double integral of fxy dx dy over R is equal to double integral of f of g of uv, h of uv. Here x and y are replaced by their corresponding formulas in terms of u and v. Dx dy is replaced by absolute value of Jacobian times du dv over g, where j is the Jacobian of xy with respect to uv, and that we will remember it is given by this determinant whose first row is del x by del u, del x by del v, second row is del y by del u, del y by del v. Sometimes this is known as Jacobian determinant also, or we can simply say that it is the Jacobian which is given by this determinant. So in this lecture we have discussed how to apply change of variables in double integrals. In the upcoming lectures we will discuss problems related to this change of variables formula. So this is all about this session. I hope you like it. Thank you very much.